Right, welcome back to STEM Online Academy. Okay, so let's get right to it today. We're going to discuss something very interesting, the electric potential of continuous charge distribution, in this case of a ring. Okay, so most students solve this problem the hard way. Okay, and that's exactly why they get stuck. Today, we're finding the electric potential of a charged ring, and I'm going to show you the smart and clever way to do it. Okay, the way that actually saves time on exams and builds a strong physical intuition. Okay, you're going to see exactly what I mean by that, right? If you've ever brute forced this with painful integrals, this video is for you. Okay, so let's get right to it. All right, so let's draw a ring. So let's go to a different. Let's go to another page here. Okay, so we're going to draw a ring. Okay, so let's start drawing a ring. I'm going to have to use an XYZ coordinate axes. Okay, color code them each one. Okay, nice. We got that. We got that. Maybe use green. This will be X. This one will be Y. This would be Z. And since it's a three-dimensional axis, okay, draw a three-dimensional axis. Because remember, we're trying to find electric potential of a ring centered at the origin. Okay, all right. So I'm going to explain that. Just give me one sec. In reality, this is what we're looking to solve. The question is, we're going to solve this. We're going to solve. This is what we want to solve today. Okay, we're going to solve this guy right here. That V is equal to 1 over 4 pi, right? 4 pi epsilon naught, okay? Integral of dq all over the square root of z squared plus r squared. Okay, this is what we want to be able to solve, right? Electric potential. All right, so let's do that. So we're going to draw a ring. Okay, so look carefully that we're integrating with respect to u. That means a continuous, infinitesimal charge distribution. Okay, now it's all over the square root of z squared plus r squared. Okay, so what we're going to do is we're going to draw a ring centered at the origin with radius r and axis z. Okay, so let's do that. Right, so we got this. Okay. And here's the axes. Okay. And then we're going to make our infinitesimal charge will be located over here. This is my dq. Okay. My dq is there, right? Right on the x-axis based off the way our equation is. Okay. And my point P will be on the z-axis. Okay, so here's my point P. My point P is always a distance, let's say d away from my infinitesimal charge, right? dq, all right? And what we need to do is, right, is we're going to draw our ring, okay? Our ring has to be along, as I said, right? Along centered at the origin, okay? Something like this. I'm going to make it. Here's my ring, okay? That's my ring, my continuous charge distribution, okay? And what I do is I draw my point P to point to my infinitesimal element, dq. Okay, like this. right, so we got that. And then the point of this is not only to draw a dashed line from point P to DQ, right? It's to make sure that there's a cancellation, okay, if you understand what I mean. Cancellation of the electric fields in this case here, okay? So you can see that right there, right? We want our setup to be right, so it'd be like this. So the distance from DQ to P, same like this. The other point of the axis here. And the point of that is to create something like this, okay, right? And you'll notice what ends up happening is that our field elements will cancel. The x components will cancel here because of the way that our line segments are intersecting, okay? All right, so those line segments here and here are going to be canceled out, okay? Right, so here's the setup, right? We have a uniformly charged ring, right? Uniformly charged ring. I can also label this capital R with radius R here. Okay, that's radius R. Total charge is Q. I'm going to call this capital Q. Okay, capital Q of this entire ring. Okay, and we want the electric potential at a point on the axis at distance z from the center. If you understand what I'm saying, okay. All right. So I've just labeled the ring, the axis, and the observation point. Right. Observation point is point P, and everything else to be self-explanatory. Right. Now this is a standard. This is a standard university physics problem. Okay, especially if you take electricity and magnetism. Okay, and it shows up constantly on exams. Not exactly this, but concepts close to this usually come up on exams. Okay. All right. So we've got that. All right. Oh, yeah, it's also mentioned something else here. Oh, and this would be my Z. Right. So this here is the length Z. It's the Z axis. Okay. So say this is Z. Okay. And you can see that we have a perpendicular bisector along Z axis and Y axis. Okay. So it's a right angle. Hint, hint. All right. Here is the issue. Here's the struggle. The common wrong approach that lots of people have. Okay. Right, so here is, I'm going to say wrong instinct that a lot of people get. Right. So wrong instinct that most people have. Okay. They say that the electric field comes from Coulomb's law. So let's integrate the electric field. Okay. Slow down before you do that. Right. Just because the electric field comes from Coulomb's law does not necessarily mean that we need to integrate the electric field. Okay. So I've sketched some messy vector components here. What I mean is this, right? These vector components, okay? This and this here that are getting canceled out, right? They may say, okay, this is an electric field vector, right? Right? And this one's another one, right? And their components, right, along the y-axis over here, right? So E sub y and negative E sub y, right? This is E sub y, the other one's E sub y on the right direction. Okay, right? And suddenly the vector components are everywhere. There's a trigonometry explosion, and then there's an algebra overload. And at this point, the confidence is going to collapse. Okay. But the problem isn't your calculus. That's not the problem. Okay. The problem is choosing the wrong quantity. Okay. So you want to choose the correct quantity. Okay. That's what I'm saying here. Now, the key idea, right, that I want to get out of the way, right away is think before you actually integrate. Okay, let me repeat. Think before you integrate. Okay, so let's go to another slide here. Okay. Notice how everything has just disappeared, right? This is one of the most important ideas in all of electromagnetism. Okay, the electric potential is a scalar. I hope you understand the point I'm making. Since electric potential is a scalar, we don't treat it as a vector, right? If we were integrating, if our problem was integrating, let's say we found, say, calculate the electric field, right? Yes, then the electric field vectors would be important, and then their components would be important, right? But electric field is a vector, not a scalar, okay? Electric field is a vector, not a scalar, okay? Electric potential is a scalar. So if symmetry exists, right, always ask, can I compute the potential first, okay? So if symmetry exists, always ask if you can compute the potential first, okay? Here, the answer is yes, and it changes absolutely everything, okay? So here's a smart setup strategy, okay? So let's go back here, as I mentioned, right? I drew a small charge element dq on the ring. Okay, so here is my small charge element dq, okay, as you can see there on my ring. All right, and this is a three-dimensional projection of what's happening to our continuous charge distribution of the ring. Let me show you really quickly what is happening in a two-dimensional projection so you can see it from a panoramic view comprehensively. Okay, so as you can see, we have in my model here, we have a potential on an axis of a charged ring. That on the left-hand side for a uniform ring, right, is a two-dimensional projection of what is happening to the ring. Along the z-axis, you can see the particle there going up and down vertically on the z-axis. Okay, as that is happening, it creates on the right-hand side here. Okay, I wouldn't say a bell curve, but some sort of curve, orange curve to the right, which the particle is traveling. So again, as you can see, right, as the uniform charge ring there, right, as the particle is moving up and down on the z-axis, right, as the particle moves down on the z-axis, it's actually going upwards on uh, on the axis on the right hand graph here. Okay, as you can see, right, and when the point, right, when the point particle is at the maximum at its top of the z-axis, right, the particle is at its one of not the lowest point, but one of its lowest descent on the right-handed orange curve, as you can see, right, and vice versa. Okay, just wanted to bring that up for a sec. Okay, let's go back. All right, so as I was saying, what's its distance to the point on the axis? Okay, what's its distance to the point? And that's what I did when I drew this, right? Remember, point P has to be separated from DQ. Okay? And you'll notice that its distance, right, from point P to DQ, this distance here is the same as this distance here. Okay. And in reality, since they're symmetric on the right-hand side, I'm also forming both of these are forming right angle triangles. So from point P to DQ, right, we're getting some length R here, a little R, I'm going to call it, right? Little R here and a little R there, right? So that's a little R. And since it's a perpendicular bisector, there's a z-axis, a z, length z on the z-axis, length capital R on the y-axis, okay? And you can see that it forms a right angle triangle, right? It's the same for every point on the ring. Therefore, little r is equal to the square root. R is equal to square root of capital R squared plus Z squared. That makes sense, right? Pythagorean theorem on this. That's the way we're going to, that's the symmetry we're going to exploit here. So no angles, no components, no vectors. Okay, no vectors whatsoever. So do not do this. This would have been wrong. Okay, no vectors whatsoever. Do not do that with electric potential. Okay. All right. Be very careful of that. If you do that on your exam, you are in serious trouble. Okay. That's only for an electric field vector. Okay. Okay, so we have this information here, right? Let's set up a clean integral here. Okay. So let's set up the clean integral on the next page based on what we have. Okay. Now, we were already given an integral to solve, which was v equals 1 over 4. So let me just put over here v. So v, the electric potential, that's what v stands for. Okay. So electric potential v is 1 all over 4 pi epsilon naught. And then we're integrating, right? The dq all over the square root of capital R squared plus Z squared, okay? Where R is a constant, okay? Be careful, okay? Well, little r is a constant. That's what, so we were asked to solve this. This comes from the fact that it starts off like this, okay? Starts off that V is equal to, sorry about V, has to be saying dV, right? dV, the differential element of the voltage, is equal to 1 over 4 pi epsilon naught, okay, or dq over 4 pi epsilon naught times r. R is constant, okay? And then from dv, we get to v by taking the antiderivative and integrating, right? That's how we get there. Since the denominator is constant, it's going to come out of the integral. Okay, so what that means is, right, the third step here, right, is to say that v is equal to 1 all over 4 pi epsilon naught, right, 1 over 4 pi epsilon naught, okay, times 1 all over the square root of r squared plus z squared, and then I'm just integrating, right, so integrate with respect to q, okay, and the integral, right, of dq over the ring is just the total charge, right? You would agree with me that if you integrate with respect to q over the ring, it's total charge, right? It's automatic. So v is equal to 1 all over 4 pi epsilon naught times 1 all over the square root of capital R squared plus Z squared, okay, times capital Q, okay? So therefore we get V is equal to, I can put this all on top, capital Q all over 4 pi epsilon naught times the square root of capital R squared plus Z squared, okay? All right. And you can see this is our final result, okay? By the way, this voltage is a function of what? I'm gonna give you to think about that. What is it a function of? Z, right? V is a function of Z. Everything else remains constant. Charge is constant. Total charge is constant. Epsilon is constant. R is constant. Z is constant. Z is not. Z is changing. So that means that we get this equal to capital Q all over 4 pi epsilon naught times the square root of capital R squared Z squared. And we found our final result. Okay. All right. So that's it. No brute force, right? No suffering, no confusion of what is what, whether it's a vector or it's a scalar, right? Just structure, okay? Right? All right, so one last thing that we need to know, two last things actually, is the physical interpretation of this result here. Okay, what's the physical interpretation? All right. So we need to do a sanity check for this. Okay, so let's do physical, physical interpretation. Okay, so physical interpretation is very important. Okay, the physical interpretation, okay, is we need to check the following. Okay, and what we have to check first is, so number one, okay, number one, we need to check when when our z, little z, is going to be much greater than capital R. Now, what that means is that the ring looks like a point charge from a very far distance. Okay, that's what this means. This means that the ring looks like a point charge. Looks like a point charge. Point charge. Okay, number two, right, is when z is equal to 0. When z equals 0. That's also important. Okay, the potential will then be finite. Okay, the potential, the electric potential is finite then. In other words, it gives us a number. It's finite. Finite. Okay, and not infinite. These are the field conditions, they're called, when it comes to doing this. And this is also correct, okay? This is also correct, right? So you can see that the mathematics, right? The mathematics here, and combined with the geometry, right, matches the physics, okay? So that's very important, right? So I just want to list some common exam mistakes before we finish up this lesson. Okay, so let me go to another page. Common exam mistakes. So common exam mistakes. Right. So anytime when you have an exam of some sort, try to make sure you're avoiding all the following. Okay. So number one, here's where students lose the most marks, right? Number one, integrating the field instead of the potential. They're getting confused with the concept. Integrating, so integrating the field. You can just highlight these. The field, field, integrating the field instead of the potential. Instead of the potential. Okay, that's number one. Number two, forgetting symmetry. Forgetting the symmetry. Okay, number three, these are all very important. Treating R as a variable when it's a constant. That's a very big problem. A lot of mistakes with that. Treating, right? So treating R as a variable, R as a variable, when it's a constant. When I should write that down. When it's a constant. Okay, and then number four, finally, overcomplicating, complicating the geometry. Okay, all of these are extremely important when it comes to common exam mistakes. So follow them to a T, please. Okay. All right. So if you just fix this one habit, choosing the right quantity, E&M becomes a much easier course. Okay. All right. Right? And this same, now I'm going to also talk about how this generalizes, okay? Right? Because it's not just for electric potential. Okay? Uh, the same strategy would work for disks, right? The disks, spheres, right? Doesn't have to be anything. Doesn't have to be rings. Can be disks, spheres, cylinders, and many continuous charge distributions. Doesn't matter. Okay. All right. That really doesn't matter. So what I want you to get from this is that you're not memorizing formulas. You're learning how to think when it comes to your physical intuition. Okay. Which is really important. Right. So before I get going, I just want to mention one last thing. Okay. If you want more problems like this, where calculus, right? As you can see, a lot of calculus here, a lot of cool stuff. Okay. We where calculus and physics intersect, or you can say work together instead of fighting with you. My book, Advanced Integration Techniques, is written exactly for undergraduates who want that edge, right? Who want that edge specifically. And if you want one-on-one help building this kind of intuition, you'll find tutoring details in the description below. Okay. If you want extra specialized help, coaching help, where I can go into real depth and help you conceptually understand hard topics, uh, this is the place to be. There'll be a link. There'll be two links in the description below for this YouTube video, and or you can always go to my main channel page, Jason Masterakos at S.T.E.M Online Academy. All right. Okay. Yeah, you'll find the tutoring details in the description. Okay. In the next video, we'll be looking at more interesting concepts. We're going to do some interplay with series and integrals. Okay, a lot of integrals. I'm going to go back to series from a mathematical perspective. Today was more on physics, but we're going to go because we haven't done physics application in a while. Well, we have, but not in depth when it came to electromagnetism. Okay, like today. But the next video is going to be on series. Okay, mathematically, right? Okay. If this helped, like the video, like and subscribe. Um, I always like to thank my subscribers, and there'll be plenty of more interesting videos coming coming soon. All right. Have a great day, guys. Thank you for watching, and again, like and subscribe.